Hey everyone. Not too long ago, I made a video about how I tried to train a neural network for hand sign detection, but ended up running into a problem known as overfitting. And this is how I describe the problem. Basically, the network is bad at making generalizations about the training data that can be carried over to the test data. Honestly, I had no idea what I was talking about. Like, I understood what the consequences of overfitting were, but I couldn't really explain why it happens in the first place. However, in my last upload, I talked about how you can use neural networks for linear regression, and in the making of that video, I sort of realized what would cause a neural network to overfit training data. And it all came down to considering whether that two-neuron network I had created was facing the same problem. And the answer is no, because of how I restricted the neural function to a linear form. What allows overfitting in general is having extra unnecessary complexity to a network. And in this video, I want to show what that would look like for a network trying to model a set of points that follow a linear trend. Let me start off by saying that this was supposed to be a simple task, but it ended up requiring more steps than I originally anticipated. But because of that, I did end up learning a lot more in the process. So I figured that it'd be a good idea to share the whole experience with you. So with that said, let's jump into it. So if you're going to try to add more complexity to the network, you'd obviously want to have more neurons, but you can't just use more of the identity neurons that I made specifically for linear regression, because if each layer affects the next layer in a linear fashion, then the overall relationship between the inputs and outputs remain linear. This is why neural networks use activation functions like sigmoid, which introduce nonlinearity to the model by altering the weighted input to each layer. But the problem with sigmoid, as I've mentioned in my last video, is that the output is restricted to values between 0 and 1, and so it becomes difficult to predict the value of y, which is part of a much wider range. I thought about combining sigmoid and identity neurons in the same network, but while that is possible, it is not easy to implement by modifying the original network class. Then I realized that I can use a different activation function that would have a wider output range while still introducing nonlinearity. One of the most popular of these is called ReLU, or Rectified Linear Units. For this function, the output is 0 for all negative inputs, and then after 0 it behaves like the identity function. So the derivative is 0 for all non-positive inputs and 1 for all positive inputs. To implement this, I made two different network classes. One called linear network, which uses the same identity neurons from the previous video, and another called ReLU network, which is almost identical to linear network except for the activation functions at the bottom, which I renamed and modified to create the behavior of a ReLU neuron. It should be noted that since these classes are so similar, using class inheritance would be a good idea, but to keep this video simple, I decided to just copy and paste the majority of the code. Now, before creating an instance of these classes, we still need to change the evaluate method because right now it calculates the coefficient of determination, and that is only applicable to linear models. I tried looking for other measurements for goodness of fit, but I couldn't find anything useful, so for the sake of this video, I just had evaluate return the sum of the squares of the residuals. This will be sufficient for looking at how the accuracy changes over time, but it should not be used for comparing models trained on different datasets. The reason why is because if one dataset has a lot of points, it will have many smaller residuals, which can lead to a deceptively large summation. So with those changes made, I started on the main script, which will instantiate and train a linear and ReLU network, and then graph the results using matplotlib. The linear network called net1 is the same two-neuron network from the last video. Net2 is the ReLU network, and it has 6 layers with 28 neurons total. For training, I used the same data from my last video and chose a very conservative learning rate over a larger number of epochs relative to the hyperparameters I used for pure linear regression. Finally, I just gathered a list of predicted y values for each network over a range of inputs and plotted them with the linear model being blue and the ReLU model being orange, and this is the result I got. Okay, so if you take a look at the evaluation results for net2, you'll notice that the error goes down in the beginning before getting stuck around 59. This is known as the dying ReLU problem, which happens when the weighted input to the majority of the neurons is negative, and as a consequence, the derivative of the activation function becomes 0, which makes it difficult for the network to figure out how to change its weights and biases to lower the cost function. So to combat this, I tried to instead use a leaky ReLU, which is almost the same as a normal ReLU, but it has a slight positive slope in the negative input region, which should allow the neuron to continue training. I changed the ReLU network to implement this and reran the code. This time the network was more successful at fitting the data, but it still looked pretty similar to the linear model. Obviously some crazy stuff happens for negative values, but that's only because ReLUs aren't designed to predict negative outputs. I thought the similarity between the models was due to the fact that ReLU behaves like the identity function for positive inputs, so I decided to look for another activation function that would deviate from that, and I ended up choosing SoftPlus, which is basically a smoothed out version of ReLU. I created another class called SoftPlusNetwork and implemented the appropriate activation functions at the bottom. Then I redefined some variables in my main script and ran again, but the new model still followed a linear pattern. But then at that point, I realized that the points I've been using were almost fully collinear, which I figured might be the cause for a network model's tendency to become linear. So I added more variance to the points and ran my script for the 4th time, and lo and behold, I finally got the graph that I was looking for. The orange curve here is a perfect example of how a network model can overfit training data. Remember that the whole purpose of training is to reduce the value of the cost function, which means minimizing the error between the actual and predicted values as much as possible. You can see here that the SoftPlus network has smaller residuals than the linear network, but it doesn't follow the overall linear trend of the data. That's because the network is only looking at the points that are given, and it doesn't care about what's happening in between. So if given enough flexibility, the model will contort itself to fit the data as perfectly as possible. When that happens, it becomes less useful for finding meaningful patterns that can be applied to new data. This phenomenon was also at play when I trained my network on the images of hand signs. Of course, the model is harder to visualize because the data contains vectors with hundreds of dimensions, but this basic demonstration gives better insight into the underlying cause of overfitting. Thank you so much for watching. As always, if you have any questions, don't hesitate to post it in the comment section. If you enjoyed the video, feel free to like, share, and subscribe, and I'll see you next time.